Dan Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos that I've been posting to the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you how I've completed some of the projects associated with the guide. So I have a video series on the forum now that shows me completing the 4 circuits associated with Project 1 and the associated coding challenges with those circuits. I also have a video series on the forum doing the same thing for Project 2, where I complete each of the individual circuits and the associated coding challenges. And the last 3 videos I've posted to the forum show me going through the individual circuits of Project 3. So the first video shows me completing Circuit 3A, which shows how a servo motor works, and I did the associated coding challenge with that. The second video I've posted for Project 3 shows me going through Circuit 3B, where we use an ultrasonic distance sensor to detect motion, or the distance rather from an object to the sensor. And in the last video I did Project 3C, which kind of incorporates everything: a servo motor, the ultrasonic distance sensor, an RGB LED, and a piezo buzzer, which creates basically a motion activated alarm system that would stop an intruder, or your cat from jumping up on the counter. And I did the coding challenge for that as well, where I incorporated a motorized Nerf gun motor that shoots a dart when an intruder gets close to the ultrasonic distance sensor. And in the last video it was running pretty long, so I didn't actually go through all the code for the coding challenge, but I just kind of gave a little demo. And so in this video I'm going to go through the code for that coding challenge, show the demo, but I'm also going to talk about bipolar junction transistors and MOSFETs, BJTs and MOSFETs, which kind of act as electrical switches that allow you to use a microcontroller such as an Arduino or the Redboard, SparkFun Redboard that came with our kits, and you're able to control high current devices via these BJTs or MOSFETs. So I'm going to be talking about that in detail. So again, if you want to check out the last video first. If you're watching this one, this is really a continuation from the previous video where I go through Circuit 3C of Project 3 in detail. I talk about, again, the fact that I created an interactive Nerf gun using an ultrasonic distance sensor, RGB LED, servo motor, and buzzer. I do discuss the some of the concepts associated with the ultrasonic distance sensor for measuring distance, as well as I talk about the trigger and echo pins of the ultrasonic distance sensor, and using the get distance function to trigger the ultrasonic distance sensor and then interpret the echo and therefore get the distance ultimately. I've discussed those further in a previous video as well, where I focused just on the ultrasonic distance sensor. We also go over the RGB LED again, which provides visual feedback of how close an object is to the ultrasonic sensor. So if you're really close, within 10 inches, it'll light red. If you're between 10 and 20 inches, it lights up yellow. And if you're greater than 20 inches, it will light up green. We also incorporate a servo motor for action. So if you're within 10 inches, the servo motor is going to alternate and toggle back and forth between 2 positions, essentially causing a paper cutout that we create that's attached to the servo motor via a linkage rod, which is really just a paper clip we've bent. It causes it to jostle back and forth, giving the illusion of movement, and hopefully would scare an intruder or scare your cat if they happen to jump up on the counter. We also use a buzzer for sound alerts, and but the main claim to fame of the last video, or the point of the coding challenge, was the use of this new component, a bipolar junction transistor, to control power to a Nerf gun mechanism. Again, these components are essentially electronic switches that we can use the microcontroller, like the Arduino or the Redboard, to electronically switch on or off these transistors, which are then attached to some high current device, like in this case a Nerf gun mechanism motor, that normally wouldn't be able to be powered directly with the Arduino. I'll also discuss the conditional statements, as always, determining the actions based on distance. So again, if you're within 10 inches, if an object's within 10 inches of the ultrasonic distance sensor, we're going to have the RGB light up red for close proximity, and that's when we're going to move the servo motor and sound the buzzer, as well as shoot the Nerf gun in the coding challenge. And if you're between 10 and 20 inches, RGB will be yellow, and we're not doing anything with the LED, the sound, or the Nerf gun. And same with if you're past 20 inches, the RGB is just going to be green, and again, the servo and buzzer and Nerf gun aren't going to be doing anything. I also demonstrate the use of the fire button, either via physical button or just if you're in close proximity, and talk about the bipolar junction transistors, the BJTs, and MOSFETs. So that's what we're in store for today. So this is the circuit I had done up in the previous video. So it looks kind of like a mess, but this here is the general circuit that you have before the coding challenge that incorporates the ultrasonic distance sensor, a piezo buzzer. I have a potentiometer here controlling the volume of the piezo buzzer. That's not in the original circuit, but I just did that so I could lower the volume if I wanted. An RGB LED, which is right now green because if there's the object in front of the ultrasonic distance sensor is greater than 20 inches. We have a servo motor, which isn't hooked up right now because I've ran out of pins, so I unhooked it in order to hook up this second servo motor, which is acting as a little plunger to push a Nerf dart through the motor mechanism, the electronic motor mechanism, in order for it to fire. So that's all part of the original circuit. That servo motor, this paper cutout of just a picture that you can choose online. They use a CAD in the circuit. I used a sassy donut. So this little circuit here is what's kind of connecting the Nerf motor, the Nerf gun mechanism motor, to the breadboard, as well as I've included an extra button just for my testing purposes. So if I want to press it, the motor will go off. Even though, so pressing it will cause the motor to go off, but really the motor's supposed to go off when you're. So really the motor goes off when you're in close proximity. So this was just more for testing purposes. Again, I'll show you the original circuit. I'm actually going to shut off the motor so it doesn't make any sound right now because it's quite loud. So the motor's off now. So, but again, if you watch the previous video, that's the sassy donut that jostles back and forth. If I tried to go close to this, I was going to put this in front of the fridge to keep me from snacking. Do not even think about having any junk food. Hopefully that was going to encourage me. But yeah, let's get right into the code. So I'll just push this off to the side for now. I'm losing things here. Okay, I just pulled out this wire into the 5 volts, and I'm not sure what that was for, so we'll have to just take a look. It might be for the breadboard. It's right. I see what it's for. It's right here. Okay. So this is the code for the coding challenge. I kind of went through it a little bit yesterday, so I'll just be quicker. Just kind of a quick summary if you didn't watch the other video. For the servo motor, you just have to include the servo library as usual. As well, for the servo motor, you need to create an object of type servo. You can name it anything you want. We've named it my servo. That's just kind of a convention, but you can name that anything. You could have named it Bob. In the setup mode, when you're dealing with a servo motor, you have to call the attach method on your object of type servo, and you pass in the pin associated with the digital pin, the PWM pin that your servo motor is connected to. So my servo motor is connected to digital pin 9, which is a PWM pin. So this method essentially just does it's like the pin mode method, but for servo motors. And then what do we do with the servo motor in the code? Well, in the loop, I've got this commented out, but in the original code, in the original circuit, the servo motor just alternates between 160 degrees and 140 degrees. So you may recall that a servo motor typically can go from 0 to 180 degrees, although it's not necessarily great to go from the extremes because your servo can get shaky and not act as expected. But in this case, we're writing the servo motor to 160 degrees using the right method, and we're going to keep it there for a delay of 100 milliseconds, which is 1/10 of a second. And then we're going to move it to position 140 degrees, so 20 degrees away, and we're going to hold it there for 1/10 of a second. And basically this is going to go back and forth between 160 degrees and 140 degrees, alternating for a tenth of a second each, back and forth, while our distance from the ultrasonic sensor is less than 10 inches. So that's the main purpose we're using the servo motor for in this circuit, at least in the original circuit. You can see I've got a commented here. So in this circuit, I'm moving a servo to 75 degrees when I'm within 10 inches, and when I'm not, I'm moving it to 0 degrees. Whereas before, in the original code, I was moving it to 20 degrees. But again, now when I'm not using it, I'm going to 0 degrees. And the reason for this is because I've unhooked this servo motor because I ran out of digital pins, and servo motors have to be on PWM pins. So I've unhooked this because I don't need the circuit going back and forth like this. Instead, I need this servo to work, which again, this servo is acting as, like I said, a little plunger that this is going to move and push the dart through if this was mounted. So again, that plunger moves. Instead, that servo motor moves when I'm in close proximity. So that's why we have that code like that. So that's the main thing the servo motor is doing. Again, if I actually press the fire button, I'm going to do the same thing with the servo motor. I'm going to move it to position 30, and that's going to cause the plunger to move. So that's what the servo motor is doing in the circuit. So now back to the top. Then this code is associated with the ultrasonic distance sensor. We've got two constants created for the trigger pin and the echo pin associated with the ultrasonic distance sensor. We've got a float variable to store the distance measured by the sensor, and that's float, so a real number variable. In setup, we call pin mode function, twice for setting up both the trigger pin as an output and the echo pin as an input. So you'll recall that the trigger pin needs to send a 10 microsecond pulse out to start the ultrasonic sensor sensing, and then a high pulse comes back into it, into the echo pin, so we need it as an input, and it comes back in, and the duration of the high pulse ultimately is proportional to the duration of time it took for the ultrasonic sensor's pulse to hit an object and come back. And we use that in order to calculate the distance. In the loop, we use the get distance function associated with the ultrasonic sensor with the code we've created, and assign that to the distance variable, and then we just print the distance to the serial monitor with the unit of measurement as inches afterwards. And then within the code we have a bunch of conditional statements, if-else if statements, to determine how close you are to the ultrasonic distance sensor, in which case we will do different things with the RGB, LED, and servo motor and buzzer, and the Nerf gun as well. So if the distance is less than 10 inches, we're going to turn on the RGB. We're going to put it to red color, so we're going to make a red light. In the original code, we're going to jostle back and forth the servo motor, but we're not doing that, and turn on and off the buzzer through tone and no tone, but we're not doing that in this case. We're just making the LED red by just writing to an analog write to the red pin and leaving the other two have a 0 value, green and blue. And then what we're really doing with this coding challenge is we're going to do a digital write to the BJT output pin, which is a pin going to that transistor, and we're going to pass it high, basically turning that transistor on. Again, using the microcontroller to control this transistor and have it act like a digital switch, so that we just turned on when an object was within 10 inches of the ultrasonic distance sensor. And then we're going to write the servo to 75 inches. We're going to call the write function on the servo writing it to position 75 degrees. Wait there for 2 seconds, and then write a low signal to the transistor, shutting the switch off. So we turn the switch on, move the servo to 75 degrees, and the switch is on for 2 seconds, and then we switch the switch off for a minute and a half. Again, why am I switching the switch off? Well, because if the object stays within 10 inches, I don't want the motor just going constantly. I at least want it to shut off a little bit. In fact, I probably should make this a little longer, but this will be fine. If the object is in front of the ultrasonic distance sensor and it's between 10 and 20 inches, we're going to make the RGB LED turn yellow by sending 5 volts to the red pin and about 1 volt to the green pin, and that combination will give us a yellow pin. We also need to make sure that the buzzer is not on, calling the no tone function, and move the servo back to the 0 position. Else, which happens if we're greater than 20 inches, so if we're really far away, we're going to make the RGB LED green by sending 5 volts to the green pin and 0 to both red and blue pin. And again, make sure the buzzer is off using the no tone function and moving the servo motor to position 0. So that's what's happening there. Again, this is the distance method associated with the ultrasonic distance sensor, which basically is a couple local variables for the echo time and calculate time. The echo time is going to be measured by the time that we get that high pulse back into the echo pin, which is proportional with the distance that the signal had to travel from the ultrasonic sensor and hit an object and bounce off and come back. So basically what we're going to do with the get distance function, we're going to send out an electronic pulse from the ultrasonic sensor that's 10 microseconds long, not milliseconds like it's written here, but it needs to be microseconds. And we do that by doing a digital write to the trigger pin, sending out a high pulse. We do that for 10 microseconds, so we call the delay microseconds function, not the delay function, which is in milliseconds. No, we want to do this for 10 microseconds, and then we write the digital pin, the trigger pin low. So we send out the pulse, and then we're going to read in the pulse that we get back, the high pulse we get back, using the pulse in function. We're going to read that on the echo pin, and it's in high mode. That's just something that you have to do. This is associated with the HC-SR04 ultrasonic sensor. It's a high mode sensor for the echo pin. And we're going to do that pulse in function and assign that to echo time. So this is going to return a time in microseconds that we had a high pulse come in on the echo pin, which again is proportional to the distance. You might recall in a previous video I talked about some of the detrimental aspects of pulse in. It's akin to using delay for button debounce. You can use delay to create a simple button debounce in a program, and it usually works for most simple programs fairly fine, but it is stopping the code from actually executing during that delay. So better coding would use time functionality methods in order to do a button debounce. And I've talked about those in previous videos. Well, pulse in has the same detrimental effects that delay does in a button debounce. So a better option would be to use time functionality, which I've discussed, and if you're interested, look at my videos on the forum, reference the ultrasonic distance sensor. But for this code, it's fairly simple. The pulse in function is going to work great. And then we're going to calculate the distance by just taking that echo time, which again would have been the high pulse that we received back into the echo pin, which is proportional to the distance. We're going to take that echo time and divide by 148. And that's going to give us a distance in inches. So again, I've went through in previous video to do the calculation for this and why we're dividing by 148, which gives us a distance in inches. If we wanted a distance in centimeters, we would divide by 58. And again, I go through that whole calculation in another video. And then we're just going to return the calculated distance. So that's all the code associated with the ultrasonic distance sensor. So far we've talked about what the servo motor is doing and the code associated with it in this coding challenge, what the ultrasonic distance sensor is doing and the code associated with it. Now let's talk about the RGB LED and the buzzer. So the RGB LED and buzzer constants are here, representing the red pin, green pin, and blue pin. They're all PWM pins. The blue pin isn't actually needed at all in this case. We don't use blue for anything, any of the colors, because we use red fully, green fully, and yellow, which is a combination of red and green. So we don't technically need this, but we've included it for completeness. Also, we never actually write the red pin anything but 255, so we could actually take this off of pulse width. We could actually not use a PWM pin for this if we wanted to, because we don't actually ever write anything besides 255, which we could just do a digital write high. The green pin, however, we do need as a PWM pin because we set it to 50 on one, meaning we're only sending 5 volts when we want to create a yellow LED. Anyway, in this case, the point is that we do have them all. All 3 of the RGB LED pins are on PWM pins capable of pulse width modulation. That's pins 3, 5, and 6. However, in this case, really only the green LED needs to be. We also create a buzzer pin constant representing the pin that the speaker is on, and it's on pin 8 here. Originally the code has it on pin 10. I've moved it to pin 8 because I'm using pin 10, which is a PWM pin that I need for my transistor, that digital switch. So I need that on a PWM pin, I want it on a PWM pin. So I've taken the speaker off of pin 10, which is a PWM pin, because you might recall from a previous video, speakers, kind of the tone function associated with speakers works sort of like pulse width modulation, but unlike pulse width modulation, which needs to be on pins 3, 5, 6, 9, 10, or 11, any of the 6 PWM pins associated with the 14 digital pins of the Arduino, the buzzer pin can be on any digital pin. Tone will work on any digital pin. So I've just kind of switched those around. Basically, I just use pin mode functions to set up all of your RGB LED pins as outputs. The buzzer pin is an output as well. And the conditionals based on the distance an object is from the ultrasonic distance sensor just controls again what color the LEDs turn and when the buzzer pin activates, which again only happens when you're within 10 inches of the ultrasonic distance sensor. We turn on for 1/10 of a second, turn off for 1/10 of a second, on, off, every 1/10 of a second, as well as the servo would be moving normally. And last but not least, the main importance of this coding challenge is I have, correction up here, I'm using that BJT as a digital switch to turn on and off a Nerf gun motor. So I've created a couple constants representing the BJT output pin, as well as just a constant for the fire button, which is that test button I have. So if I want to activate the motor without waiting for something to be within 10 inches, I can do that. I just set both those pins up as using pin mode function, set up the BJT pin as an output pin because we need to send a signal to the BJT because BJT is a current controlled switch. Essentially, we send a little bit of current to the base and it opens up the switch and allows lots of current to flow through a collector and emitter, which I'll get to in a bit what that means. We also set up the button as an input. And I didn't put input pull-up or anything because I'm actually using physical hardware to create a pull-up resistor. So I just set up as an input. But if you weren't using a physical resistor like I am, you could do input pull-up and use the internal resistors associated with the microcontroller. But I don't need that. And then I just write the digital pin low just to make sure it's in a low state because I don't want the switch turned on from the start. I just outputted a message to the serial monitor. And here's what we do. So when we're within 10 inches of the ultrasonic distance sensor, this code is going to cause the digital pin to the transistor to go high again, as I said before, turning the switch on. We move the servo motor to a particular position, and that's that little plunger servo motor that's going to push a Nerf dart through the motor. We do that for 2 seconds, write that high, and then we write it low for a second and a half. Those timings are just arbitrarily chosen. And that's pretty much it. I also, in addition to the close proximity alarm, I also made it so that if I just press the button, if digital read of the fire button equals low, because it's normally held high because I'm using a pull-up resistor to pull it to 5 volts. So if it's low, that means it's been pressed. Well, if it's been pressed, I'm going to do the same thing that I would do if an object was within 10 inches of the ultrasonic distance sensor. I'm going to turn the pin high that's going to that BJT digital switch. move the servo motor to a particular position, turn the red LED on, which it should be on anyway if I'm in close proximity. I'm going to output fire button press to the serial monitor just for my own visual cue in case I have the motor off, because sometimes I shut it off because it's very noisy. I'm going to do that for 2 seconds, write the motor high, turn on the transistor, BJT transistor high, therefore allowing the motor to work for 2 seconds, and then turn it low and turn off the light. And the 50 millisecond delay is just so that we can read things in the serial monitor. So again, that's a lot of code just to say that this is what's happening here. I'll turn back the external power source on the motor. So you'll notice that I've got an external power source being used to power this motor. So it's a 9-volt power source, positive negative leads here, and that's because this motor wouldn't really be powered very well with a microcontroller, and it could also damage things. So we'll talk about that here in a moment. But again, if I had an object within 10 inches this would fire a Nerf dart at someone, and the plunger, again this plunger, would just push a dart out. So I'll try to hold this and show it. Really I need to mount this somehow so that this does it properly, but the Nerf dart goes in here, and you'll notice if the motor goes off and the Nerf dart's in there, you won't even hear the motor. It'll seem like it's not going off because it's not powerful enough to suck this dart through. Obviously in the original gun there was a way that something pushed on the dart as it was going through because it's not strong enough otherwise. But so if you see, the motor actually is going off. It's just with the dart in there it doesn't sound because it gets stalled. So we do need this servo motor to act as a plunger. I'm going to try to hold it and see if I can simulate what a plunger would do. So see, I'm going to activate this thing and we're going to watch this plunger move and push the dart through. So I kind of moved my hand and it didn't stay in position, so you do have to be careful and hold it in position. I really should take the time to mount this, but this is for demonstration purposes. So I've got that held there. I'm going to try to activate and we'll see what happens. So yeah, I pushed out most of the way, but not quite. Not quite. So that could be two things. One, I might need to adjust the code a little bit. Play around with the plunger, although I don't think that's it because it was working yesterday. But instead of having it go from, let's see, when I activate... where am I here? When I'm within 10 inches... I move the servo to position 75, so right now it's at position, I guess 180. I move it to position 75 and leave it at 0 when it's not being activated. Well, instead, maybe what I need to do is move it all the way to 90 or something like that. So let's try this and see if that makes any difference. So we're going to move now, not from 0 to 75, we're going to move to 90, so moving this all the way through. I might even go as far to move it to 100, and we'll see if this does a difference, because it's just going to cause the servo motor to move more. So I'm going to move this out of the way so we can see what's happening. So this now should move a lot further. I'll just show you first by activating it. Once the code uploads, of course. So you see it moved all the way up to there, quite a bit. So it's moving all the way up there. That might be too far. We'll see. Okay, I'm going to try to activate it. So the problem is I keep moving my hand as it pushes. I think definitely that's too far, so I think 90 would have been max. So we'll try 90, and then I'll just show you by pushing it through. But really, you would just use this and you'd fiddle, and you'd have to have this mounted in a certain way. If you did a linear push, that would be even better. So where am I? I'm writing it to 100. I think 90 is kind of the max I should do. Maybe even 85. Let's try that. So put the dart in. Have this mounted here. And activate. Okay, so that worked a little bit. It's kind of difficult to do it at the same time. So maybe I'll show that in the next video. Now I'm just going to show you how it works if something actually pushed it. I'm going to push it when it spins. I'm also going to up the time that it's spinning, just so I have more time to fiddle. But again, you'd obviously want to mount this properly and have that plunger right in the right way. Maybe attach a little more to the end. I just kind of attached this quick, whatever this was, like a little thing off of one of my kids' toys. But, you know, you might want to set that up a little differently. But I want to show you, because it actually shoots out at quite a high speed. So I'll show you that. So I'm going to push it at the same time. I'm going to get in a position to do it. Okay. This is really difficult to demo. I'll try one more with this dart. Hopefully I can demo it better. Where did the dart go? So once the motor gets going, this is what happens. Anyway, we'll come back to that later because that's not the point of the video right now, but that's the live demo. Let's go. I'm just going to shut this down, unplug this, and I'm going to show you how that BJT works in the first place. So, if you go to the Drone Workshop website, or just Google Drone Workshop, MOSFET, and BJT, it shows you an excellent resource online for doing that. So if anyone's familiar with Drone Workshop, they have excellent videos on YouTube, and then associated articles. So I'm just going to go through one of those articles. So I've made some notes of my on my own, kind of a summary, and these are kind of the schematics and circuit diagrams and pictures that you can expect from them. So we'll go through it and then we'll do them. So Arduino high current interfacing. So high current interfacing, basically what the whole point of the MOSFETs does is so that you can allow high current devices. So let's see. Arduinos are excellent microcontrollers, but they can only control low current devices. So in order to extend that capability of your Arduino and allow it to drive higher current loads, we're going to use transistors and MOSFETs with our Arduino. So as you guys probably know, the Arduino is a microcontroller. So the name microcontroller means that its primary purpose is to control things. That's the controller part. And micro means it's a very tiny device. So it's tiny in more than just size, however. It has a small current capability, okay, limiting its use to directly controlling only small devices. things that only take a small amount of current, like single LEDs, OLED screens, and LCD screens. So again, it's a microcontroller, and it can only control micro currents, essentially, so from these small devices. So that's where BJTs and MOSFETs comes in. So these, this is an image of BJT and MOSFET in a T0222, I think, or 220 package. We'll get into that in a bit. So, however, this limitation of a microcontroller hasn't stopped us from controlling much larger devices like gear motors and large stepper motors. And how do we accomplish this? Well, we can either use a driver board, which I think I've shown in some previous videos, when it comes to the motors, and you have a motor board that came with your kit, which is ultimately what you're going to use to create your autonomous robot car. And so we can use driver boards to take low current Arduino control signals. Again, the current coming from an Arduino control signal that we're sending out is low current, but we can use that to drive the high current motors. In these cases, the driver board did all of the heavy lifting for us. But how is that possible? Well, really, the driver board accomplished this using transistors and MOSFETs. So when I'm saying transistors and MOSFETs allow us to take the tiny bit of current that the microcontroller can send out in their digital pins and control high current devices, but then I also said, well, driver boards can also control high current devices. It's because they're using transistors and MOSFETs as their underlying technology. So the Arduino itself is in fact a collection of transistors on a single chip. So transistors and MOSFETs. This is just some history, the guys who invented it. In 1956, there was a Nobel Prize in Physics awarded for their work on semiconductors and the transistor theory. And basically, transistors are the basis of virtually every electronic device today. The laptop or smartphone you might be watching this on, or your TV for that matter, everything. So all the advances in medicine, space research, the internet, everything. I mean, electronics are ubiquitous in our lives, and transistors are at the forefront of that. They're the basic building block. So transistors replace vacuum tubes correctly, and they could act as either amplifiers or electronic switches. We're mostly going to be using them as electronic switches today, but they can also be used as amplifiers. So there's a couple different types: BJTs and MOSFETs. So in my coding challenge circuit, I'm using a BJT, but this article and the corresponding YouTube video associated with this will go over both the BJT and the MOSFETs. So the standard transistor is the bipolar junction transistor, or BJT. So these are a couple of facts. There's two main types, NPN and PNP. Watch the video, it'll give you a little more detail on that, or you can Google that. It's kind of getting down to the chemical level in that and the materials used. Not necessary for using them in this case, besides the fact that we are using an NPN, which is kind of the more common. It talks about the different leads. There's a base, an emitter, and a collector. The base is where I was sending my output signal to. So in my Arduino code, I was writing the output to the BJT signal high and low when I wanted to turn on and off. Well, I was outputting that signal to the base. So a BJT has three leads: base, emitter, and collector. And I've color coded them like that for a reason, because the base is taking the low current from the microcontroller, which I'm indicating with blue, current like water, low current from the microcontroller, and turning on the switch, essentially allowing the switch to be turned on. So it's basically current controlled switch. And then the collector would have your positive leads from your motor and different things connected to it. The negative leads from your motor, but your motor and everything would be connected to the collector, which is why I have it in red, kind of like that's where your power stuff is coming from. And the emitter is connected to ground. So like that. And this arrow kind of indicates in what direction things are going. There's two types, as you see in the diagram, NPN and PNP. I'm not going to be really discussing them too much. Suffice to say that we're using an NPN, and that is the more common type. So BJTs and MOSFETs. BJTs are current driven. So you have some low current source, i.e. a microcontroller, sending out a signal via one of the digital pins, and that is what is going to the base and that is turning on or turning off the switch depending on if you're sending a high or low signal. But again, it's a low current source, like a microcontroller, an Arduino, or your breadboard, is turning on this digital switch. And when you turn on the switch, it then allows the high voltage and current power. So again, you got high voltage and high current power device, like a motor or something, or a lamp. And then it allows it to now connect and go through. So before, consider this as open when this switch is turned off. So we've got this high power and voltage current source going to a load, and then that load would normally be connected to ground, and that would allow that load to be turned on. You would get we'd have a complete circuit. But if this is open, it's not connected to ground, so the load doesn't turn on. As soon as low current, the sufficient amount of low current goes to the base of this transistor, it effectively turns it on, allowing this connection to happen, and then current to flow down to the ground. So a BJT is a current-driven device. So it's current-driven. That is to say, it is switched on when current flows between the base and the emitter. So again, the Arduino will send a signal through the pin, which is current, and that will go to the base and effectively turn it on, so that creating a connection now between the base and the emitter, which now the collector, which already touched the base, can now get to the emitter, which is ground. So it basically completes the circuit. A sufficient current flowing into the base will switch on the transistor and allow current to flow between the emitter and the collector. So again, high current is allowed to flow between the collector and the emitter when we have a low current signal, a sufficient low current signal on the base, thus creating the connection and allowing there to be a connection between the collector and the emitter, therefore completing the circuit. When the BJT is switched on, it behaves a lot like a diode. In a way, you can think of it as a switchable diode. And a diode is just something that allows current flow in only one direction. Kind of like our LEDs, which are light emitting diodes. They're a special type of diode, but they only allow current to flow in one direction. You might remember from earlier lessons in the SparkFun Inventors kit, it talks about how LEDs are polarized and need to be put in the breadboard in a certain way because they have a positive-negative lead. Well, that all refers to the fact that current can only flow in one direction. Unlike something that's a non-polarized component, like a resistor, in which case you could plug it in any which way. So that was BJTs, which is what I'm using in my circuit challenge with the Nerf gun. However, there's another type of transistor, the MOSFET. So MOSFETs are a special type. They're a metal oxide semiconductor field effect transistor, so it's a special type of transistor, just like the bijunction transistor was a special type. And the MOSFET has many improvements on the BJT in many ways. So it's a high impedance device that uses low voltage to switch it on. So whereas the BJT used low current to switch it on, this uses low voltage to switch it on. As with a BJT, a MOSFET has 3 leads. They're named different things, but it still has 3 leads. It has a gate, which is like the base of the BJT, the thing that we're sending the voltage to, the low voltage, in order to turn on. With the BJT, we sent a low current signal to the base to turn it on and allow current to flow, high voltage current and to flow from some source down to ground. It flowed between the collector and emitter. Well, in this case, if the gate gets activated via low voltage, then current's allowed to flow from the drain to the source. So the drain is acting like the collector of the BJT, and the source of a MOSFET is akin to the emitter of the BJT. So it's kind of good just to have that comparison. So again, MOSFETs, that stands for this metal oxide semiconductor field effect transistor. 2 main types, an N-channel and a P-channel. Just like you had an NPN and a PNP, the 2 types of BJTs. Here you have an N-channel and a P-channel. Again, that just refers to the material, which we're not going to get into. Again, N-channel is the more common. There's 3 leads. Again, gate, drain, and source. So again, the gate, and this is an N-channel, and the P-channel. And again, the drain is up here, and the source is connected here. So again, the gate would be like the base of the BJT. The drain would be like the collector of the BJT, and the source would be like the emitter of a BJT. 2 types, N-channel and P-channel. And the MOSFET uses a low voltage source connected to the gate. Again, low voltage source. So remember, the BJT used a low current source to turn on the transistor. The MOSFET uses a low voltage source. So when a sufficient voltage is applied to the gate, the MOSFET is switched on. Just like with the BJT, when a sufficient current was applied to the base, the BJT was switched on. So low voltage applied to the gate. So in this case, you can see low voltage applied to gate, indicated by the color. This allows current to flow between the drain and the source. So now current will be able to flow between the drain right here and the source, therefore completing the circuit. The MOSFET acts like a very low resistor when it is switched on. So again, when you have sufficient voltage to the gate, and therefore switching on the MOSFET, you have very low resistance between the drain and the source. Very low resistance, which means it allows a lot of current to flow through. Low resistance means you can have a lot of current. So, since MOSFETs have a very low on resistance, they don't dissipate very much power, so they stay cool even without heat sinks. So that's another advantage of the MOSFETs. Because they have very low resistance, they don't dissipate very much heat. Because remember, resistance is heat. So because you're resisting current flowing, so it's the resistor is what takes that abuse by resisting that current, and it heats up. If you ever touch a resistor, especially if you don't have one rated for the voltage and current that you're using in your circuit, the resistor will get really hot, possibly burn. Again, if you have a lot more going through than it's rated for. So, whereas in this case, because we have such low resistance when we turn on the gate, there's low resistance, it doesn't allow for much current. Or correction, it allows for a lot of current, but the low resistance doesn't dissipate much heat. Which means you don't need a heatsink. Which, by the way, if you're curious what a heatsink is, it's just a piece of metal that gets hot to protect components. And this little thing here on the transistor, this little piece of metal is designed, there's a reason there's a hole in it, it's designed so you could screw that on and attach it to a heatsink. So this could be attached directly to a heatsink. So, we've now learned about BJTs and MOSFETs. What's the difference? When to use one and all that sort of thing? Well, whether the answer, whatever transistor is best for your design, isn't straightforward. Both the BJT, the bipolar junction transistors, and MOSFETs have their own strengths and weaknesses. So here's the differences, and then you'll decide based on your circuit. BJTs are current controlled. Okay, they requires biasing current and limiting resistors. So you need limiting resistors because it's current controlled. MOSFETs are voltage controlled. There's no biasing current or limiting resistor. So right there you have less components in that sense. You don't need that limiting resistor. And again, you have less heat dissipation, that sort of thing. And again, this is Ohm's law coming into play here. So BJTs have lower impedance, so therefore they draw more current. Because again, lower impedance draws more current due to Ohm's law. If you remember that from earlier on, this relationship, Ohm's law, voltage equals current times resistance. Current is represented by I. And if we rearrange the formula, we have resistance equals voltage divided by current, and we can see they're inversely proportional. The denominator on this fraction is equal to R in the numerator position. So they're inversely proportional. As the resistance goes up, current goes down, or vice versa. If current goes up, resistance goes down. So lower impedance, i.e. lower resistance, impedance is, kind of think of it as resistance. Lower impedance means more current. Whereas with a MOSFET, it has high impedance, therefore it draws minimal current. So it's not drawing very much current. Because again, resistance and current are inversely proportional. So BJTs also have higher gain than MOSFETs. You can get higher gain, which is required for amplifiers. So you'll remember earlier on up in the PDF here, it said that BJTs were used as electronic switches and amplifiers. We're not going to be using them as amplifiers in our cases, but they could be, and the higher gain helps with that. Well, that's what an amplifier needs, to amplify something, to gain something. And again, MOSFETs have lower gains than BJTs. BJTs have a larger internal size than MOSFETs, so MOSFET is smaller size than BJTs, which again, another advantage. However, BJTs are less expensive, so MOSFETs are more expensive. So that's one of the disadvantages. Again, MOSFETs have a lot of advantages on BJTs, but if cost is a factor, then BJTs are going to win out. As you can see, in most applications, the MOSFET has some distinct advantages over the BJT. But in some cases, like in the design of amplifiers, then you'll need a BJT because it has higher gain than MOSFETs. Or where cost is a factor, then the bipolar junction transistors can be a better choice because, again, MOSFETs are more expensive. Our transistor MOSFET. So the thing that we're using in this circuit, in my coding challenge, I have a TIP 122. So in this tutorial, in this video by DroneBot Workshops, they're using a TIP 120 Darlington transistor, which is just a type of power transistor. I'm using a TIP 122. There's virtually no difference. It's just a little bit different tolerances as far as and thresholds for voltages if you look at the data sheets. But for all intents and purposes, especially for what we're using it, they're interchangeable. So again, I'm using a TIP 122, but works about the same. It can switch loads up to 60 volts. So again, I think the 122 has a higher switching voltage. So that's one of the differences. And it can handle peak current of 8 up to 8 amperes, and a continuous current of 5 amperes. A Darlington transistor just means that it's a pair of transistors that are actually in the same package. So it's just two transistors together. So the emitter of the first transistor, which would normally be the thing that goes to ground, is connected to the base of the second transistor. And the collectors of both transistors are connected together. That's a Darlington pair. But that's beyond the scope of this tutorial and what we need to do. And the package that this transistor is in a TO220 package. That just means it looks like this type of transistor here. Because there's different packages. There can be smaller ones like this, but this is a TO220 package. Also, I didn't use this in my coding challenge, but he also goes over the IRF 520 MOSFET in the video, which is a power MOSFET. This MOSFET has low gate threshold voltage of 4 volts, and because of that, it's commonly used with microcontrollers like the Arduino for switching high current loads. So there is actually a better one that you can get. When I looked up, you can get an IRF-L, or I believe it's IRL 520. It's the same number, there's just an L in there, which stands for logic, meaning it's meant to be used with logic devices. And so I think its threshold voltage is a little lower because, microcontrollers only output max of 5 volts. However, this IRF 520, even though it's not exactly meant for logic controllers, it's easily able to be accommodated considering the low gate threshold voltage, meaning the voltage you have to send to the gate to turn it on, turn the MOSFET on, is 4 volts. And we know that our microcontrollers are capable of outputting 5 volts, so we can easily use this MOSFET to control other things. So it's commonly used with microcontrollers like Arduino for switching high current loads. Again, it comes in N-channel power MOSFETs. That's what this one is. The gate threshold voltage is 4 volts max, which is why we can use it in microcontrollers. So again, commonly used with Arduino. And it's got a 220 package too. So it looks just like this one. Both of them look the same. You just have to get magnifying glass out and look at the number to see what you're dealing with. Popular MOSFET module. In the video, he also uses a module, just a low-cost module you can get online, that has a few supporting components in addition to the MOSFET, like screw terminals for power and that sort of thing, 3-pin connector for the Arduino. But you could accomplish the same thing he does in the video just using the discrete components, the actual individual MOSFETs and resistors and all that stuff yourself. But he uses a module. Modules often make things a little nicer to work with, and they're very cheap online. So now we're going to talk about some of the experiments. So Arduino with transistors. So I just explained kind of what a MOSFET is and BJT, and we're going to be using the BJT. So now let's actually show what they've done in the video. So again, if you look on their video online, just Google YouTube video of DroneBot Workshop MOSFET and BJT, and it'll pop up. But I'm just going to go through the experiments with you that they do in the video. So the first couple of experiments, we're going to use the TIP 122 Power Darlington BJT. I'm going to use they're using the TIP 120. I'm going to use the 122. Again, it just has a little higher threshold, the 122 does, but it doesn't really matter. He's going to be using a 6-volt batteries for his loads and experiments. You can use any DC power source up to 40 loads, but strictly DC power. Do not try to do this with AC at all. Do not use alternating current, i.e. the power that comes from your house if you plug something in. Don't use that. Use a battery, something that's not attached to the house. Use a battery source, an external power bank, or just an external battery pack that came with your kit, something like that. So only DC power, up to 40 volts. But again, 6 volts, 9 volts, stick in that range, I would say. So the first experiment we're going to create is a basic Arduino transistor switch. So here's the image. There you go. So this is what we're doing first. We're using the TIP 120. That's a basic transistor. We're going to be powering a light bulb, have a 6-volt external battery source, the microcontroller. You can use the red board. They're showing an Arduino board here, but the red board is just an Arduino generic board. A couple resistors, I believe a 10 kilo ohm resistor for your pull-up resistor, a push button, and a 2.2 kilo ohm resistor. But yeah, so the first experiment is we're creating a basic switch to control a load with a transistor and an Arduino. Again, that's often what BJTs and transistors are used for. They're like digital switches, electronic switches that we can use to turn things on and off without actually pressing a push button or a physical button. For my high current load, I'm using a 6-volt incandescent light bulb. That's what they're doing in the experiment. I'm using a 6-volt light bulb as well, but I just stole it from a flashlight. So normally the flashlight uses 6 volts to power this light bulb, and I just took the spare bulb out and am doing that just to make it a little smaller. You can select another resistive load if you want, but again, the point is it's a high current load. So the microcontroller would not normally be able to control it. So we need an external power source, in this case 6-volt incandescent light bulb, so 6-volt battery with an incandescent light bulb. So he's shown everything hooked up. It's right here. And then I'm going to show you as well. So first I'll show you the diagram. It's got the microcontroller. He's got the TIP 120. Again, I'm using a 122, but it's just the same thing, a BJT transistor. Into the base, we're going from digital pin 9, so it's a PWM pin, going through a 2.2 kilo ohm resistor into the base. Again, this is where we're going to send a signal out, and this low current signal from the microcontroller is going to activate the switch. It's going to turn it on and off. We've got from the 6-volt power supply, the positive end of our light bulb, so our positive wire, red wire, is going to hook into our 6-volt power supply, and the ground wire from our light bulb, or whatever resistive load you're using, is going to go up into the collector. Okay, so this middle pin is the collector of the TIP 120 or 122, depending what you can get on Amazon. So it's going in there, and then it's going to be allowed to flow down through the emitter only when the base gets activated. So if it comes in here, it's going to go down through the emitter, and instead of going straight to ground, it is going to go to ground, comes here to a combination, it goes to ground. So again, 6-volt battery supply is going through this light bulb, through the collector pin, and it can only get through the emitter and down to ground, and therefore turn on the light bulb, if at the base we have a sufficiently low current source to turn this switch on. But assuming we do, we go to the ground. We also have the negative connection of our external battery supply connected to the same common ground, and one end of our push button is connected to that common ground. Now the other end of the push button is connected to through the 5 volts is connected through the 5 volts pin of the Arduino through a 10K resistor. So this is a pull-up resistor pulling the state of the button high when it's not pushed. So when it's not pushed, it's connected to ground and 5 volts through the resistor, so it'll be reading as 5 volts on digital pin 3, which is an input pin. If, however, we press the push button low, then if we push the push button, we're going to go to ground, and therefore we'll be reading a low signal. So that's what the circuit diagram looks like, and this is what the actual circuit looks like. So I'm just going to move this out of the way. So I've got two circuits on here at once, so I'm just going to cover one up so it doesn't distract you. Just going to move this out of the way. Again, this is for the next circuit. And these two wires here are going to connect up to our external power supply. So this rail is going to get, I guess I'll put 6 volts on it, maybe 5 volts on it, I think, for this light bulb. And the negative. So you won't be able to see that on the screen because I'm going to move it off. But again, this is just an external power supply. And this second part of the circuit is for after. So this is the first part of the circuit. And we'll start by uploading some code to it. So first I'll just I'll get some code going here. Okay, so as you can see, this is code from DroneBot Workshop. I just downloaded this right off the website, and it's just the transistor switch demonstration. So they've created an output pin to the transistor, so that's the same thing I'm using in my coding challenge. So this output pin to the transistor, again, is going to this base right here. So again, it's going to that base. That's where the output pin goes. And then we have a constant for the button pin, which is pin 3, and a button value constant. In setup, we just set up the pin modes, creating the output pin as an output pin, the button pin as an input, as usual, and we're going to digitally write the output pin low, just to make sure it's low at the start, and therefore not activated. In the loop, we're just going to constantly be reading the digital, we're going to call a digital read on button pin, and assign that to button value. If button value equals high, which means no one's pressing the button, because remember, it should equal high by default because we're using a pull-up resistor to pull it up to 5 volts. So if the button is not pressed, we're going to turn the lamp off. We're going to use digital write to output a low signal to the output pin, therefore keeping the transistor off, the digital switch off. And we're going to do that for a 20-second delay. This delay is just acting as a button debounce. Again, just a simple debounce. Else, meaning button pin's value is low, meaning it's been pressed, then we're going to turn the lamp on for 5 seconds. So we're going to call digital write function, sending a high signal to the output pin. I'm also just going to indicate that on the serial monitor just so we know when the button was pressed. And we're going to leave it high for 5 seconds before turning it low. So it's just going to turn the light on for 5 seconds. So we'll plug this in. Okay, so we're just uploading the code. I'm going to turn the serial monitor on just so we can see. Okay, so we can see that, and again I'll just show you. So from the orange wire here is connected to digital pin 9, a PWM pin, and it goes connected right here and then goes through this resistor, this current limiting resistor, which is a 2.2 kilo ohm resistor, into the base pin, so the first pin there of the transistor. And if you can look up the data sheet, the pin out for this, and that is the base pin. And then we've obviously got 5 volts and ground connected into the breadboard rails here, just so we can use them. We've got, from the other end of the button, we have one end of the button connected to ground. Actually, it's technically, if you can see it there, it goes through that gray wire and then through that little brown wire, and it's connected to the third pin on this Darlington transistor, that third pin. And what that does is that's sending it to ground, because remember, this third pin is the emitter, and that's going to ground. So we're basically sending one end of the button connection to ground, as per the schematic we've seen, and the other end is going through this resistor, 10K resistor, a pull-up resistor, into a power rail. So again, by default, when this button's not pressed, we're pulling it to 5 volts, and when it's pressed, it'll get connected to ground through the emitter, which is connected to ground as well. And then we'll be reading off of this yellow wire, which is also connected here with the 5 volt power. We're going to be reading it on digital pin 3. Now if you look in the back here, again, we've got power hooked up to this circuit, an external power source hooked up to the power negative here. And that's different than the microcontroller. And we've got the positive lead of this incandescent bulb from a flashlight, a camping flashlight. We've got this positive lead hooked into the positive voltage source, and then the negative lead is connected directly into the collector, which is that middle pin of that transistor. So it's connected into the middle pin, the collector. So again, just to show you the schematic for that, again, from the Arduino, 9 volts going through 2.2 kilo ohm resistor into the first pin, which is the base, and then the button is hooked up, one end is hooked up through a 5K resistor, or sorry, to the 5 volt power source on the Arduino power pin, through a pull-up resistor, and is going to be read on digital pin 3. The other end is connected to ground, and again, emitter is also connected to ground, as is the negative terminal of our external power source. And our incandescent light bulb, one end is connected to the external power source, the other end goes into the collector. So again, that's what we have going on there. And so how does this work? This is a part of another circuit. If I press the button, the light will turn on for, if I press the button, the light will turn on for 5 seconds as per the code. Try to get the code up there. And what's happening is when I press this, again, we're doing a digital read. If button value equals high, when it's not pressed, we just keep the output pin low. Else, when the button is pressed, because else would be it equals low, which means it's pressed, we're going to send a high signal to the out pin, which is this orange wire going through this 2K resistor into the first pin of our transistor here, which is the base. So we're sending a low current source to the base, thereby activating this switch, which then allows the external battery source that's going through this red wire, and then the negative wire of this light bulb goes through the collector, and then emitter is connected to ground, the next pin, but that's not connected. The collector, the middle pin and the right pin are not connected unless we get a high signal through this transistor, turning on the switch. And even then, how do I get that high signal? Well, I do it by pressing the button. Pressing the button will cause the switch to turn on. So again, pressing the button causes the light bulb to turn on for 5 minutes as per the code. Again, I'll upload the code if required, and pictures of these circuits if you guys want, but that's essentially what's happening there. So we'll move on. And again, that's his circuit, looks similar to mine. Push button, pull, you can see the push button here, pull up resistor to the power rail. The other end is connected to ground. The signal wire is going to digital pin 3. This red and green wire are just causing this power and negative rail of the breadboard to be connected to 5 volts and ground of the Arduino. This yellow wire, so what he's doing with this yellow wire right now, this yellow wire which is hooked up through this 2.2K resistor into the base pin of the transistor, this should be hooked into digital pin 9, but he's unhooking it right here. If you watch the video, he's going to put it into the power rail of the 5 volts of the Arduino, basically acting as if when I press the button, it causes a high signal to be sent from this wire, thereby turning on the transistor and allowing current to flow from the collector to emitter, turning on this light. That's if I press that. But what he's doing is he's testing out the function by removing this wire. And instead of relying on the button being pressed, he's just removing this wire from pin 9, which will get a high signal when the button's pressed, and he's just hooking it directly into the power rail, like this. By hooking into the power rail, you always have a high voltage, 5 volts on the transistor, and therefore have it on effectively all the time. So that's what he's doing there. I'm just going to plug that back in. And now it just works with the switch again. Okay, so moving on. So that's the circuit. So note that in addition to the Arduino, the TIP 122 or TIP 120 or 122, what I'm using, a light bulb and a battery, you'll also need a button switch, a couple of resistors, a 2.2 kilo ohm resistor, the current into the base to limits the current into the base of the transistor, while the 10 kilo ohm resistor is a pull-up resistor for the switch. Again, this is a pull-up resistor for the switch, and this is just a current limiting resistor to limit the current going into the base. This is the code. I've already shown you, but basically it's just the code for a BJT acting as a switch. We use a push button. Nothing too special. You can look through it. This is going if the button value equals high, then the button is not pressed and we don't do anything. We just keep a low signal on the output pin. So again, why, if it's high, it's not pressed? Well, that's because we're using pull-up resistors hold the button high when not pressed. If we had used a pull-down resistor and had a resistor going to ground, we'd have the opposite. It'd go high when you press it. So it just depends. Kind of pull-up resistors is kind of the default you think of. In fact, if we didn't use a physical resistor, we could have used in the code when we called pin mode function in loop, we could have went pin mode button pin comma input underscore pull-up. If we changed this second argument to input underscore pull-up, it would activate an internal 20 kilo ohm pull-up resistor that we could use, and then we wouldn't have to have a physical resistor in our circuit. Again, that's just another part of the circuit. So if it is high, then the button has not been pressed. So again, the button value variable, if it's high, the button has not been pressed because the 10 kilo ohm resistor is pulling the input up to 5 volts. If the button is pressed, the input will go to ground and the value will be low. And then we're passing current to the transistor base. That's what's causing the switch to turn on. And it turns on a light bulb. Now we're going to talk about switching inductive loads. So that was a resistive load. This light bulb is a resistive load. If we're going to switch inductive loads, there's a little extra things that we need to know. The arrangement we just saw with the transistor and the Arduino works well for resistive loads. But for inductive loads, there's another consideration. An inductive load refers to any load that passes electricity through a coil. That would be motors, relays, and solenoids. But what's most particular does is motors, because we're using motors in our projects in general in order to move the wheels associated with our autonomous car that we're going to be creating as the last project. But also I'm using a motor right now in this challenge in order to shoot a Nerf dart. So when current is passed through a coil, it creates a magnetic field. Small currents generated in the opposite direction. And this is sometimes called reverse EMF or backflow voltage. And a device like a motor or solenoid can have a large reverse electromagnetic field. Again, this current that's generated in the opposite direction that we don't want. And that reverse voltage can damage transistors, so they need to be protected from it. So again, the transistors we're using, in the case of this this tutorial, I'm using a 122. He uses a 120 in his video, but that would be damaged by this reverse voltage. So we need a way to protect ourselves from it. Now, the most common method of protecting from reverse EMF damage is to use a diode wired in the opposite polarity. I repeat, wired in the opposite polarity that absorbs this reverse voltage. Having it wired in the opposite polarity essentially lets this back EMF naturally go through that diode and therefore not destroy your transistor. So, in this experiment, we're going to use an inductive load, i.e. a small DC motor. So the same transistor, though, the same BJT, bipolar junction transistor. And you'll see there's a lot of similarities. We're still using digital pin 9 to activate the base, again sending a small current to the base, which will turn the resistor on or off, acting as a digital switch. We're still using a current limiting resistor, 2.2 kilo ohms. We have still an external power source, 6 volts, and the positive end of our battery, or correction, of our motor is connected to that 6 volt power source, and the negative end is connected to the collector. That was the same as our light bulb. The positive end was connected to our power source, and the negative end was connected to the collector. And then it would go through the emitter if and only if the transistor was activated by a current going to the base. So again, it would go to the emitter, which would ultimately connect to ground, and the negative side of the external power source is also connected to ground. The thing that's different is we have this flyback diode, so this rectifier diode, which is there for protection. So, but you'll notice that this little line here, you might not be able to tell, but the negative side is right here, which is connected to the positive side of the battery. And the positive side of this diode is on the negative side of the battery. So it's in the reverse order. And the reason for that is because when this stops working, when the motor shuts down for a second, normally the power is going through the motor this way from positive to negative. When the motor shuts down, it's going to cause this back EMF where it's going to want to, electricity is going to want to flow back into the transistor and destroy it. So this diode, this protector, allows electricity to flow through it the proper way, in the way that it's oriented, positive, negative, and therefore not destroy this transistor. The potentiometer is just hooked up here, one terminal to 5 volts, one terminal to ground, and the middle wiper terminal to one of the analog inputs. That's just done to control the speed of the motor, because we're going to send a PWM signal using analog write through digital 9 and turn on. We could just turn the thing on and off, but then it would be at 6 volts and then 0 volts, 6 volts and 0 volts. So the motor would be at full speed and no speed, full speed and no speed. Using a PWM pin and a way to control it, i.e. a pot, we're able to control the speed of the motor. So note that the diode across the motor leads. I used an IN4004 rectifier diode in this video, which is a very common device, but it has to be in the opposite polarity. They've also added a potentiometer again to control motor speed. Again, this is just showing the Arduino code, and he controls a motor that way. So we're using analog write command to send PWM signals to our transistor. And again, we're using PWM with a motor. That way we control the speed, but we'll still get good torque even at slower speeds. So we'll still have good turning power at the lower speeds by using PWM. So these are just the pictures, him controlling a motor. Just remember, though, that we are losing 0.7 of the volts from our external battery. So if we have a 6-volt battery, we're losing 0.7 of a volt through the transistor. So when I mentioned that there was a threshold voltage, a certain amount of voltage that needs to go and current that needs to go into the base to turn it on, to basically activate, it's 0.7 of a volt. So not quite a full volt, but that's the threshold voltage you need just to turn on this transistor and then have it, allow current to flow through the collector and emitter. So you do lose that. So if you have 6 volts that you're planning on powering a motor with, well, in order to power the transistor, turn it on and off the transistor, you are losing 0.7 of a volt. So the voltage drop, threshold voltage required to turn on the transistor. So before we go to that, let's just look at our circuit. Actually, correction, so this is the next thing. As we've seen, this was the hookup, and this is what his hookup looks like. So I'll show you mine. Okay, that side by side doesn't work at all. Okay, so hopefully you can see my circuit and that circuit, and you'll see the difference. So now you can ignore the first part as before, but I'll just remove it. Understand that this part of the circuit is associated with the first example, and this is the second example. So in the second example, I'm going to use digital pin 9 as well. Although, just so I can keep this one hooked up, I'm just going to use digital pin 10. Again, it just needs to be a PWM pin. In fact, I'll probably use actually pin 5 because it's closer and I've got a short wire. But again, I've hooked up my wire that's going through a oh, I just noticed something. There's no transistor in the circuit, which is going to prove to be a problem. So I'm going to steal the transistor from my previous circuit that's in the coding challenge. Unhook the power. These transistors, by the way, are extremely sensitive to electrostatic discharge, so make sure you have like a ESD strap or something, or just touch a piece of metal before you fiddle with this. So I'm going to plug this into the circuit so that the left pin, which is the base, gets hooked up to this green wire, which is my signal from a PWM pin. I'm using pin 5. They use pin 9, but I'm already using pin 9. And the middle pin is the collector, and then the end pin is your emitter. Okay. And I put this in the completely wrong spot. So I need to put it here because through my wire, I'm going through this green wire, which is from a PWM pin from the Arduino, then through this 2.2K resistor, and that's where I want the base pin. So again, if you look here, I'm going through a PWM pin. They're going through 9. I'm just going to be going through 5. Through a 2.8K resistor into the base pin. So that's what's happening here. Through the green wire, through the 2.2K, and in there. And then you can also see that I have this rectifier diode, this diode, that's in a pin over from here. So it's going to be in what's the collector pin. It's between the collector pin and what's going to be the positive voltage. So this orange connects the positive voltage of the external battery source. So again, it's going to be in the reverse polarity as opposed to everything else, which is allowing for that protection. And then this gray pin just connects to the ground power source. This is going to be connected up to the emitter. So I'll just put that in. Okay, and then this potentiometer, one end connected to the 5 volts of the Arduino, the other end connected to ground. And I'll just put the potentiometer pin on A0, which is what they have in their schematic. Oh, I just realized I have the wrong image up. My apologies. So but again, digital pin still going through a resistor into the base. The positive end of the motor is going to come in through. And for the motor, I'm going to use this bad boy here. I've just hooked up one of the motors that came in our SparkFun kit with one of the wheels. Put it on this little stand. And I'm going to put the positive connection. So from the into the power source, because you can see the external power source is connected through the positive end of the motor, just like here. The positive end of the motor connects to the positive end of the power source. and the negative end goes into the collector pin, which is this middle pin here. I can put it right in the front so you can see it there. It's in that middle pin. And again, the negative lead of the motor is connected into the collector pin. We've got the rectifier diode across it for protection. And the emitter pin is connected to ground through that little gray wire, as well as the negative of our external battery source is connected to ground, because this ground is connected to this ground, which is connected to the Arduino. So, and I got my potentiometer, you can see over here, connected to 5 volts of the Arduino and ground via these rails and through analog A0. So now let's just look at the code for that. So it's fairly simple code. Again, we're just setting our out pin as 5 because that's the one I'm using. They use 9 in the video, but I've kept my old circuit hooked up. This is the one from the original demo. I'm using A0 as my pot pin. I've created a variable for the speed. In setup, I'm just using one function, pin mode, to set up my output pin as an output. You'll notice I don't have to set up my potentiometer pin A0 as an input, because if you remember, the analog pins are input by default, so you don't actually have to call pin mode on them and set them up. In loop, I'm just calling an analog read on my pot pin, A0, and I'm taking that value and assigning it to speed value. Remember, this will return a value between 0 and 1023, because there's 10-bit resolution, 2 to the 10, which is 1024, which means 0 to 1023, because we always start counting at 0 as computer scientists. So we're going to read a value into the speed there, but I don't want to send out a PWM from 0 to 1023. I can't. Remember, PWM pins, which is what I'm sending to the transistor through this green wire, which is on pin 5, the PWM pin, I'm sending it through the green wire through this 2.2 kilo ohm resistor into the collector pin, the first pin there. I need to send something between 0 and 255. 0 and 255 represent 0 volts to 5 volts through the PWM pin. So I need to call the map function to map my speed value, which is between 0 and 1023, to a value between 0 and 255, and that'll become my speed value. I could do this all in one line of code, but first I'm using the code off the website, and second of all, it's a little more explicit what's happening doing it this way. Sometimes more steps, more code is better for readability. And then we're going to do an analog write. So here we're doing an analog read to read the value from A0 on the potentiometer. Now we're going to do an analog write, sending a signal through the PWM pin. So on the output pin, we're going to send the speed value, whatever that value is, based on the potentiometer. And then we're delayed for 20 seconds. So it's very simple code. We're going to upload that. Let's plug in our board, upload that code. It's probably hard for you to see the motor, but I'll let you know if it's spinning or not, if you can't see it. I guess I could theoretically lean it back a little bit. So the code's almost uploaded. Okay, so it's done uploading. So now you'll notice the motor's not moving at all because the potentiometer, which is controlling the speed. Remember, we're reading from the potentiometer a value, and then we're mapping that value, which is going to be between 0 and 1023. We're going to map that value between 0 and 255, which is what we're going to send out through the green wire, through our PWM pin 5, to the transistor, turn the transistor on. But not just turning it on by a certain amount. We're controlling the speed of the motor. So the more I open up the potentiometer, the faster the motor goes. So let's open it up all the way and let all 6 volts go into it. So that's full speed of 6 volts. I can slow it down by putting it halfway, and it'll be about 3 volts. Slow it down more to about 1.5 volts. And then turn it off. And again, slowly turn it back on. So again, I'm using the transistor to control this inductive load. And again, the reason I have some extra circuitry here, i.e. this flyback diode, this rectifier diode. It's a protective mechanism because an inductive load causes back EMF. So if I was just using the original setup, like I was with the resistive load, the light, when I shut off the motor, especially if I have a lot of voltage and stuff going through it, like a higher mode, right? Then it's going to send back EMF through the transistor, ruining the transistor possibly. And again, these are very sensitive and possibly ruining your controller, so you just got to be careful with that. So we'll shut that off. And this doesn't work, so I don't have this hooked up. I could theoretically have these both working at the same time, but just amalgamating the code. I haven't chosen to do that, but that's pretty much what's going on there. Shut off that power source. Okay, so let's quickly get back to the code and finish talking about the rest. So, finally, Arduino with MOSFET. So, we haven't used MOSFETs yet. Both my examples do BJTs. I'll just talk about Arduinos with MOSFETs. I didn't bother doing that example simply because I didn't have a MOSFET or an RGB strip, which is what they do. But Arduino with MOSFETs. MOSFETs have a number of advantages over BJTs, which we talked about. They do cost more, but they're much better at power dissipation and simplicity in hooking them up to your logic circuit. So if you want better power dissipation, i.e. you don't need a heat sink necessarily, and you want simplicity with your logic circuits, MOSFET's the way to go. Costs you a little bit more, but it's worth it. In this example, they're going to use the IRF 520 N-channel power MOSFET, so it's power MOSFET, and they're particularly going to use a popular MOSFET module, so they're not going to be using a discrete MOSFETs like we are. We're using discrete BJTs here, like little individual elements. So I'm not going to go through this, but if you watch the video, it'll let you control an LED light strip. I don't have one. But again, you'll notice that the MOSFET looks just like our BJT. They look identical, right? You just have something different in the writing. They do have different pins, gate, drain, and source, but they're akin to base, collector, and emitter. And in this case, he's using a module. There's some additional stuff, additional 1K resistor associated there on the MOSFET input, the code. So again, I'm just seeing if there's anything I mentioned here that's of value. Use serial monitor is optional for troubleshooting purposes. That's always just a good call. And conclusion. So the conclusion of this article is that by using BJTs and MOSFETs, we can extend the control capability of our Arduino projects. We no longer are limited to devices under 40 milliamps. But they cannot be used to control AC devices, so don't even try. So again, the whole reason we went over this video is using transistors, MOSFETs, BJTs, is so that we can extend the capability of our Arduinos. We're no longer limited just to controlling devices under 40 milliamps, like little tiny servo motors or LEDs or something. We can actually control high current devices like motors and anything, incandescent light bulbs, big ones that take like maybe 9 volts, or 12 volts or something. We can control high current devices, but again, do not do this with AC devices. There's other ways to do that, and that'll be in other videos and stuff online, but it's beyond this course. I can also, if anyone's interested, just let me know. I also made my own notes associated, so I basically highlighted his article, but I also made my own notes associated with the video. I thought this guy did really good, but I just kind of highlight some things. 2 types of transistors, bipolar junction transistors, which are switches, the MOSFETs, BJTs, again, 2 types, 3 leads, base, emitter, collector. Again, BJTs are low current applied to the base, and it allows high current to flow through the collector and emitter, so it's a low current switch. MOSFETs, they have 3 leads, gate, drain, source, and they're voltage driven. So BJT is current driven. Voltage driven is what a MOSFET is, and they're efficient for controlling high current devices. Same code. Ensure the correct orientation of the diodes when connecting inductive loads to prevent damage from back EMF. So that's using that protector diode if you're using inductive loads like motors, but make sure you have the correct orientation. Remember, it's the opposite polarity as to the motor itself. Use heat sinks to dissipate if you have a lot of heat. Common applications of BJTs for controlling lamps, used as a switch, kind of like we did here with that little flashlight bulb, but you could control a larger lamp. Driving motors, so to control small motors. Automated doors or robotic movements. So again, BJTs just act like digital switches. So lots of uses. Common applications of MOSFETs, driving RGB LED strips, and things with higher current requirements. Motor control, similar to BJTs. MOSFETs can be used to control motors that require precise speed control through PWM. In summary, both BJTs and MOSFETs are essential for interfacing high current devices with the Arduino. So the choice between which one you use, the BJT or a MOSFET, just depends on your specific requirements of the project. And then I've got some, this is Arduino code and explanation example for a project I haven't quite finished, I'm working on. I was kind of extending the coding challenge to not just having a Nerf dart shoot when an intruder is there. I was going to try to create two separate modules, each with their own Arduino and own NRF24L01 RF transmitter. I've used those in previous videos to have wireless communication, and I was going to have one set up with a joystick that controlled two servo motors that I mount this Nerf gun motor on, and be able to press a button on one module and wirelessly have it fire the Nerf gun on another module. So I'll go through this in a later video if I actually finish this, but that's essentially what I'm doing. So that's what this code is for. And I was planning on doing it for this one, and then just kind of went down the rabbit hole with what MOSFETs were and BJTs and that sort of thing. But I'll go through this code eventually. I've pretty much got it working out, but that'll be for a later time. But and this is one of the reasons doing this, by the way. This coding challenge is why I dived down into having to figure out what MOSFETs were and BJTs, because I got this Nerf gun idea in my head because I was looking at a flyer for Black Friday, and it just it got me doing that. But a couple things, I'm just still going through it to see if there's anything pertinent. MOSFETs are used for the Nerf gun motor. Flyback diodes across inductive loads like motors to prevent voltage spikes. Fuses and current limiting resistors also mentioned. This is a pinout that I'm using for that circuit, so I just created this little pinout so I don't screw things up. The big thing on the Nerf firing mechanism, I need to hook up my external battery source through the MOSFET drain. The gate is hooked up to a pin 12 of the Arduino. I don't need a PWM pin, I'm just turning it on or off. That's triggered by the Arduino to power the Nerf motor. Drain was hooked to the positive lead, source hooked to there. So I don't think there's much more to say. Thanks for watching. Hopefully you learned something. Leave some comments if you have any questions. And if the comment is that these videos are too long, I know I'm not a YouTube creator. I'm only posting videos because for the course, just so you can see a fellow student do some of the projects. Thanks.